Okay, we're going to revisit gravitational potential energy now. If you remember earlier, we wrote gravitational potential energy as simply mgh. Okay, however, that is an approximation. Okay, the true equation for the gravitational potential energy is actually given by GPE, and this is equal to negative G m over some r. So if I have an object of mass capital M, another one of mass lowercase m, then the gravitational potential energy between the two, if they're separated by some distance r, is equal to negative G m over r. Okay, we'll show later on that the mgh, okay, that we've been using all this while is a simple straightforward approximation of this particular relation. Okay, but anyway, so what we understand is that the gravitational potential energy is negative G m divided by r. Now once we have an expression for the gravitational potential energy, okay, we can now proceed to figure out the total energy that a satellite has, okay, that a planet has in going around a star. Okay, so if we were to look at let's say that we have a star of mass ms, we have a planet of mass mp, goes around in a circular orbit of some radius r. Okay, then we already have an expression for the speed v. I hope that by now you all know how to obtain the speed v, even if you do not remember it. It is equal to g times ms over r, okay, the square root of this, and from here we can figure out the kinetic energy of the satellite, of the planet, and also the potential energies we already know now. So let's find the kinetic energy first. The kinetic energy of the planet is 1/2 mp times v square, so it is square root of g ms over r, and I square this thing, okay, and this ends up being equal to 1/2 times g times ms times mp over r. The potential energy, on the other hand, due to gravity, is equal to negative g ms mp over r. Okay, so now we can write our total energy. The total mechanical energy is the kinetic plus the potential, that is 1/2 g ms mp over r minus g ms mp over r. Okay, if you see, we have two similar terms here, so I can factor that out. That is the g ms mp over r multiplied by 1/2 minus 1. Now half minus 1 is nothing but minus half, so this term here is negative half, so I can rewrite this as minus g ms mp over 2 times r. So the mechanical energy for a planet that is bound to its star is basically negative of g ms mp over 2r. In fact, if you see, this is nothing but negative of half times the kinetic energy, sorry, the half times the potential energy. Okay, the negative sign here implies that the system is bound, okay, to the planet, or rather the planet is bound to the star. Now if the total mechanical energy were positive, then we know that it could escape, it could be gone, and doesn't have to be bound to the star anymore. Okay, so that's something that we'll use when we find something called the escape speed for a planet. Okay, so this gives us the potential energy, the mechanical energy in this very simple form. It is negative g ms mp over 2r. Now, like I said, we can also figure out something called the escape speed for a planet, or rather for a satellite for a planet. Okay, we can't really make the Earth escape the sun, but let's say that if we had the Earth here, which is mass of the Earth, and we had a satellite of mass some ms that goes around the sun. Okay, or actually, you know what, let's do this, let's put it on the surface of the Earth. So we have a satellite that is of mass m that is lying on the surface of the Earth. We ask the question, with what speed do we need to kick this object from the Earth in order for it to escape the Earth completely? So we want to find the escape speed for the planet, the escape speed for this mass m that is lying on this planet of mass me. Okay, now what we'll do is we're going to use energy considerations for this thing. When the satellite of mass m is lying on the planet, we know that its kinetic energy is 0. However, it has some potential energy, and the potential energy is the one due to gravity. And what we'll do is we'll write that as negative g times me times m divided by r, okay, when it's not moving. Now, on the other hand, no, we made a mistake here. What we want is we are kicking this thing, so it is moving in the beginning. It is moving at 1/2 times m times v escape squared. My bad. Okay, so this is how it's moving. Okay, so in the beginning it is going to have some kinetic energy. We're going to give it that kick. It is going to have this potential energy, and it is going to be gone really far away from the planet. Now, if you look at the expression for the potential energy, as this r becomes larger and larger and larger, okay, the value of the potential energy becomes smaller and smaller. In the limit, as r approaches infinity, this value becomes 0. Okay, so the potential energy term becomes 0. So we know that. So this is the potential energy term very far away. Okay, so very far away. On the other hand, the kinetic energy, now let's look at that. Now we want this thing to just escape. We want it to just be gone, not come back, and just escape. So what we can say is that let the kinetic energy term simply be 0. Anything more than this and it's definitely gone, but this is the lowest possible value it can have. The kinetic energy will be 0. So we have this. So now from here we can simply calculate this escape speed for the planet. So the v escape square, now I can move it to the other side, g m over r. Okay, the m's cancel out and the 2 can move to the other side, and I have v escape square is 2 g me over r, and now we can write our v escape as equal to square root of 2 g me over r. Okay, let us calculate the value, the escape speed for the Earth. So for the Earth, okay, v escape is equal to square root of 2 times 6.67 times 10 to the minus 11 multiplied by 5.98 times 10 to the 24 divided by r, and at the radius at the surface is simply going to be equal to this. Alright, we can calculate this number. So this value ends up being 11181.9 meters per second. So it's about 11.2 kilometers per second. So this is a really high value, and for the Earth, this is the speed with which you must kick something at the surface. Okay, I mean, we're assuming, of course, that there is no air resistance. So if we were to account for that, it would have to be a larger speed, and plus we also have to account for the fact that when it's moving at that speed on the Earth, it's going to heat up, it may burn, all kinds of things may happen. So the engineering itself is more complicated than this, but this gives us a limit, a value. Okay, anything less than this and it's not leaving the Earth. That's just how it is. Okay, so that's what we got.